That makes the anion. And then you work it up with acid to neutralize the base, since it's an anion, and that gives you then the neutral product. And that's the product that you isolate. So the corresponding oxo esters are also referred to as 3-oxo esters, or in the general sense, the class of compounds where you have 2 carbonyl functions flanking an sp3 hybridized carbons. They're called beta dicarbonyl compounds. Okay? And there are many examples of them. Here's the Claisen product. Okay? And there's a molecular model of it. You can see the 2 hydrogens here. Here's the ketone carbonyl. Here's the ester carbonyl. You can do this for just ions. Okay? 2,4-pentane-dione, also known as acetylacetone, common name, has this CH2 function next to 2 carbonyls. A diacid, this is propane dioic acid, common name is malonic acid. Same thing, it's got 2 carbonyls that pull on these protons here. And you can have any combination thereof. Okay? Where you have carboxylic acid and ketone or and the like. You can even have nitriles. In fact, you can have any, if you have any group that is electron withdrawing potentially by resonance, flanking a carbon, any 2 groups flanking a carbon in the middle, it'll make these hydrogens very, very acidic. And the reason is, as usual, inductive and resonance. Inductively, if we just focus on the dione, these 2 carbons of the carbonyls are delta plus, so they pull, and then in the corresponding anion, you can delocalize to the left and to the right. Okay? In the ester, the Claisen product, same thing. You can delocalize to the left, and I've just delocalized to the left here, or to the right. If I were to ask you which resonance structure is favored of the 2 that are delocalized, you would immediately tell me clearly this one, and that's why I've written it, because the carbonyl function is a better resonance acceptor because it's a hotter species. Over here, this oxygen compromises the resonating ability of the CO double bond somewhat. Okay? So it's not as good a resonator. So here's a table of the pKa's, and don't memorize anything, but this gives you some feeling for the variety of groups, and of course there are many more that one can think of. And the bottom line is they all hover around 10. Okay? Now remember, that means that these hydrogens are more acidic than the hydrogens in alcohol and in water. Okay? Meaning that if you take any of these compounds and treat them with alkoxide or hydroxide or any mild base like that, carbonate, it will deprotonate quantitatively. Okay? If you do sodium hydroxide, the equilibrium will be 10 to the 5 to the enolate side. And that's why in the Claisen reaction, the Claisen condensation reaction, you need stoichiometric amount of alkoxide. You need the alkoxide to do the coupling first, but then you need 1 mole of alkoxide to deprotonate to drive the equilibrium. And so it's not catalytic in base, unlike the aldol, which uses sodium hydroxide in catalytic amounts because you don't use up the base. So here you're actually using up the alkoxide. The demonstration that the initial Claisen addition, namely at this stage here, okay, after the addition elimination, deprotonation, addition, and then elimination, to make this intermediate, is actually endothermic, is provided by using substrates that you have to make in another way, that we'll learn about in a minute, that bear no hydrogens at these positions. And if you take these guys and expose them to sodium alkoxide, in this case ethoxide, and ethanol, these guys will unravel and go back actually to the uncoupled to the corresponding esters. Okay? In other words, another way of putting this is if you start from here and attempt to do a Claisen condensation of this, you can make the enolate here by deprotonating, do addition elimination, that would give you this, but that's uphill. Okay? And this guy has no protons available between the 2 carbonyls to drive the equilibrium. So it's stuck. It's stuck such that if you were to take this in an NMR tube, add sodium ethoxide, and stare at any changes in the spectrum, absolutely nothing would happen in your spectrum, because this would be the dominant, the only visible species in your NMR solution. Even though it's setting up an equilibrium by all these intermediates that we've drawn here to this Claisen product, they're all high energy and they're there in minuscule amounts, fractions of a percent, so you don't see them. And conversely, if you were to start with this guy, as I started leading into this discussion, and treat it with sodium ethoxide, this guy will go actually back to here. It will fall apart. Okay? Because it's unstable. You come into the equilibrium from this side here, and you go back, okay, with the blocking. Okay? And so the way this goes, you can see clearly it's just the reverse of the Claisen addition product process that we've shown here. So with ethoxide, it attacks the carbonyl, you get addition, the O- kicks back, it kicks out the leaving group, which is the enolate, and then the enolate gets protonated, and you just go here. Okay? Which is another way of saying that starting from here, setting up the equilibrium lies on this side and not on the Claisen product side. Okay? Now one can do cross-Claisen condensations under certain circumstances. In general, we can't. That is totally analogous to the cross-aldol reaction. If you have 2 different aldehydes, you get a mixture of 4 compounds. The 2 independent aldehydes will react with themselves, and then they will react with each other, with either one function as the enolate component. And that's totally identical to a mixed Claisen condensation where you use 2 different esters, the modification being, of course, on the left of the carbonyl function. So that you have an ester with 1 alkyl group and then another alkyl group. When you mix those, you get mixtures. You can get around that the same way we did get around that for the aldol reaction. Namely, you can use as one component an ester that cannot be enolizable, that cannot function as the precursor for an enolate. That blocks that pathway. So for example, formic ester, derived from the smallest carboxylic acid, formic acid. It has a hydrogen here. It doesn't even have a carbon there with a proton that can be deprotonated. And you can't deprotonate this proton. You can't deprotonate aldehydes to make the acyl anions because the acyl anions are bad campers. Again, it's a negative charge in an sp2 hybridized orbital. So this can only function as the recipient of an enolate attacking. And so you can mix this up with a normal, quote-unquote, normal ester where you can make the corresponding enolate, and then sodium ethoxide, ethanol, and after aqueous workup, gives you the corresponding Claisen condensation product. Okay, so you have CH2 minus here, addition, elimination of ethoxide. Out comes the 3-oxo ester. Okay. Good yield. These are all good reactions. Here's another case where we have a benzene ring. This also has no alpha hydrogens. Okay? So it can't do a self-condensation, and it can't act as an enolate precursor. So you mix that up with a normal ester. Now I've made a methyl ester, just to indicate you can change this R group here as you wish. Okay? As long as, of course, there is a hydrogen next to the carbonyl, so you can make the enolate. Okay? And that enolate attacks additional elimination. Out comes, after acidic workup, the corresponding 3-oxo ester. In both of these cases, there is the off chance that the ester will attack itself. In other words, the enolate derived from here or from here will attack its own precursor ester. So to get around that, often you use a component that is more reactive. This carbonyl is more reactive than this carbonyl because this carbonyl has a proton, this carbonyl has a methyl. Methyl is a pusher, stabilizes that. So in competition, the enolate derived from this, being faced with either this carbonyl or that carbonyl, will prefer that one. Similarly here, that phenyl group with this carbon pulls somewhat electrostatically, and there is also resonance which actually stabilizes this carbonyl. So here, I shouldn't say similarly. In here, the trick to use is, in order to avoid this guy attacking itself, is to use this guy in large excess. That's a trick we've used frequently when we were worried about self-reaction of one of the components. But this will work quite well, 71% yield. Now, one can also use ketones as enolate precursors, either as stoichiometric enolates, and you do additional elimination to an ester, and you get the corresponding Claisen product. And in some cases, this also works with catalytic base. So the way this works here, to differentiate the two components, is the following way. Remember that a ketone, when exposed to base, can undergo aldol by its enolate. But the ketone-aldol addition is reversible, and it's endothermic. So it's a dead-end street. So you can't ignore that. So instead, it will attack here, do an additional elimination, and make the product, because the product is the anion derived from this particular material. In this case, they use sodium hydride, which actually preforms the enolate, and then you're home free. Anyway, either way, when you use acetone, for example, as a ketone component with any other ester, you get the corresponding dione. So in this case, this is the way that 2,4-pentane dione is made. If you vary the R group here, it becomes this. So this reaction with acetone is a general entry into making diones, where this can be any R group, more or less, that you want, any ester that you're starting off with. So don't memorize any of this. The point is that you can make 1,3 diones by the Claisen reaction, and retrosynthetically, it means that you can cleave these bonds such that one component becomes an enolate component, and the other one is an ester. Okay? So you have basically, you can think about this as an acyl cation equivalent, okay? Reacting with an enolate anion, if you think in Coulomb's law, to make this bond. And the equivalence to an acyl cation stems from the fact that you have a leaving group in the ester. And so then you can write the corresponding precursor molecules, and then you have to look at the details of the molecule to see, is this feasible? Or what I have is an unsymmetrical ketone, so you have the problem that enolate formation is not selective, and the like. Okay. Now, where there is an intermolecular reaction, there's always an intramolecular reaction, and so this clever dick here, so-called Diekmann, so to speak, named it after himself. This is simply the intramolecular version of the Claisen condensation. So now you have a diester, has to be symmetrical. If it's unsymmetrical, that is, for example, you have an extra methyl here, you'll get a mixture, because both sides can act as the enolate component. But when it's symmetrical, it doesn't matter whether this carbon is red or this carbon is red. Okay? So I'm artificially doing this one. Additional elimination gives this guy. Okay? And here's the bond that you're making. And again, it's a 1,3 dione or beta dicarbonyl type component. And then you can do some really wild reactions, as this one shown here, where you do first an intermolecular normal Claisen. This enolate here attacks here, additional elimination, and then you do a Diekmann. In other words, the intramolecular follow-up to close up here. This is a contrived example, I grant you that, just to show you how far you can go. It's contrived because this is a very special dione. These two carbonyls jack each other up in terms of reactivity, and this component can't form an enolate. Okay? So it can only be the recipient of attack. Okay? And of course, this is symmetrical. Okay? But these things work well, 80% for this highly functionalized species. Okay, so how can we use these guys? The utility stems from the very fact that the Claisen condensation works. Namely, these protons are very acidic. Okay? So the initial Claisen products, and several of them are commercially available, quite cheap, can be used as enolate precursors for substitution chemistry. Okay? You can readily deprotonate, and as we pointed out, the pKa being 10, you can use sodium hydroxide, and it stoichiometrically deprotonates and gives you the corresponding anion. Those anions, unlike normal enolate anions, are unusually stable and unusually non-basic, okay? Because the negative charge is delocalized into two carbonyl functions. Yet they can act as nucleophiles in SN2 reactions, so you can alkylate. Okay? And the beauty is that the basicity problem of normal enolates is gone. So you can use now your whole spectrum of SN2 substrates that goes back to chapter 6 with impunity. No E2 to worry about. Okay? So here's how this works generically, or in an abstract way. You deprotonate with base, hit it with a haloalkane. If there's still a proton left, as shown here, you can deprotonate again and hit it with a second alkyl group. Okay? So you can put in two alkyl groups at these positions. And this is particularly useful for the Claisen products, as we just discussed here, the oxo esters, because you can deprotonate, put in an alkyl group, and then you can hydrolyze the ester to the carboxylic acid, which is only stable at room temperature. When you warm up such oxocarboxylic acids, they spontaneously lose carbon dioxide. So you get rid of the ester function. And the net result is actually formally an alkylation of the enolate of a ketone, selectively at that position, with impunity with respect to E2 side reactions. So here's some examples of these alkylations. Here is the initial original Claisen product that we got from ethyl acetate, sodium methoxide, methyl iodide, puts in methyl. Then you use another base, or you can use the same base, sodium methoxide. The literature used tertiary butoxide, probably because this is a stronger base, and they wanted, I don't know whether this is just a little slow with sodium methoxide. You can use sodium methoxide again. Yeah. Notice that the change, this is of course allowed because this guy, being a sterically hindered alkoxide, will not do transesterification. So I like this example to remind you of the fact that tertiary butoxide is a sterically hindered strong base, like LDA, not as strong as LDA, but sterically hindered. So nucleophilic reactions are very slow with this guy. So this will selectively deprotonate without exchanging with the ethoxide. Be that as it may, use sodium methoxide. That's fine. You get the anion, you benzylate now, and you get the disubstituted species. Okay. Remember, this cannot be made by direct Claisen condensation. So this is how we made the substrate that we used a little earlier to demonstrate that the Claisen will go back if you start with a species like that in the presence of sodium methoxide. So you can do this for this diester. This is commercially available, diethyl propane diarrhea, or common name diethyl malonate. You make the anion with ethoxide, and now here's an example in the literature with a secondary haloalkane. This would eliminate like a shot if you were to use a normal enolate. But here, it does perfectly good alkylation, 84%. And so we have this business that we can alkylate, and then we can hydrolyze these esters. And in the case of the oxoester, it gives the carboxylic acid. When you heat those, you get the corresponding ketone. So in a roundabout way, you've affected the alkylation of a ketone without elimination chemistry. And you can also do this for the diester. You hydrolyze, and one of these carbon dioxides blows out, and I'm drawing it on the left, because this is a carboxylic acid that also has, at the beta position, a carboxy group. And that's the essential feature for this decarboxylation. And the reason for that is that the mechanism of the decarboxylation is facilitated by this carbonyl through, again, a 6-electron transition state, where this beta carbonyl, the 3-oxo position, grabs the proton of the carboxylic acid. So the whole thing lines up as shown here, such that you have the 6-electron array, perfect aromatic transition state, functioning. You can write it by electron pair going out, pulling off this proton. As it pulls on this proton, this electron pair falls into here, which makes the carbon dioxide. At the same time, this electron pair goes here. And that makes carbon dioxide, and the initial product is actually the enol, which then, of course, tautomerizes to the ketone. So this is the beginning of what we'll discuss next week, of a very useful synthetic methodology to go around the enolate anion problem that we usually encounter with aldehydes and ketones. So let's leave it at that. Have a nice weekend. See you next week.